Welcome to the 8th Annual Air Toxins Under the Big Sky Symposium. And it's good to see everybody here. We have so far Libby, Big Sky, and Sentinel in the house. And like I said, Corvallis will be showing up here in just a few minutes. This is a special time for us. This is kind of the culmination of a year's worth of hard work by you guys. And it's this event is kind of twofold. For one, it's the culminating event of a year's worth of research, and you guys get to get up and present your findings in front of not only the other people in your class, but the other classrooms from across the state of Montana that come to this annually. And then this is also a way of us thanking you guys for all the hard work that you have done. So we hope that you guys have fun today, and don't be stressed out. It's going to be fun. Once you're done with the presentation, it's you know, we're all in the same boat. It'll be a lot better, a lot more calm. So enjoy it, and let's have some fun with it today. So we have a special guest today that's going to give the official welcome to the University of Montana. So Dr. Andre Holian is the director of the Center for Environmental Sciences for Biomedical and Pharmaceutical Sciences Department, and he is my immediate boss. So I'm on my best behavior today. But Andre has been up here at the University of Montana since 2000, and he created the Center for Environmental Health Sciences. He came up from Texas most recently, and he's a professor of toxicology. So let's welcome Dr. Andre Holian.
Well, usually I don't need a microphone. It's my pleasure to welcome you here to the symposium. You're coming up for a reason?
I was going to look for volume control.
Okay.
So let's see here. Microphone.
So, as Tony said, I've had the pleasure of being the Director of Center for Environmental Health Sciences, and it really all began from my high school experiences in the end. But before I forget, you have in your packets, you were given information.
Excuse me.
That's okay. Just to make use of the time. About the University of Montana. Please review that information. When you have a chance, take it home, and I hope you consider, I think we all hope you consider coming here to the University of Montana. It's a great educational environment. I grew up in a very small town in northwestern Ohio. It's ready to go? Okay. Well, I said, I grew up in a very small town in northwestern Ohio, and about 2,000 folks. My graduating classes were around 60 to 70 students in each graduating class. And my fondest memories, I guess this is the Corvallis group that's coming in. My fondest memories are, in fact, of my high school teachers and one English teacher, and who was actually a brother of one of the science teachers. And those memories, those fond memories, are because they really inspired me. They inspired me in the same way that we're hoping that this whole process inspires you to consider, to really appreciate the scientific process of coming into the room in an orderly fashion. All right, settled in. The teachers really encouraged me, the science teachers especially, encouraged me to think out of the box, to be creative, and to do inquiry-based learning. And they fully supported that. And that really wound up being from these high school teachers then, wound up being a lifelong lesson that I've been able to carry through the whole time here after high school, in college, and on my graduate degree and postdoctoral training and as a faculty member, is to really be always to actively question the world around me, no matter whether it's science, whether it's politics, whatever process is involved, that you're going to be involved in the future. Coming up with your own answers, delving into the topic, whatever it is, questioning it constantly, and using this information to break down the next door, the next barrier. Last week, Dr. Ward and myself had the privilege of going to a science education meeting sponsored by the National Institutes of Health. So please raise your hands. How many of you know what the National Institutes of Health are? That goes for you judges too. Okay? The National Institutes of Health is the main research funding and conducting research and funding research. It's a $30 billion industry that's supported by your tax dollars, your parents' tax dollars, more likely, that helps open the doors to improve our status of our health, testing drugs, and coming up with information. But they're also very actively involved in the science education process. One of the things that we heard last week is that the United States is falling behind in its competitiveness to other countries. Some of those are surprising. China, Brazil, others. We now rank 20th to 30th amongst countries around the world in our scientific competitiveness right now and our productivity. In really being able to understand the logical processes that go into creative thinking. And there's a lot of concern with that. And so they're really trying to bolster up these type of activities. In fact, that's what this program is really all about, is giving you the opportunity, the same opportunities that I fortunately had when I was in high school, to really do the creative thinking and to integrate that creative thinking into other activities that you have here, as far as English, putting together a presentation, thinking about it, math. It's all an integrated process. It is really our hope that this continues for you to be a lifelong process as well. There are many challenges out there in the world in human health that remain to be answered. There are many problems out here even in Montana. There's concerns with obesity, diabetes, heart problems, cardiac diseases, vascular problems, neurological problems. Many of them are impacted by the environment. There's a saying that I heard for many, many years from the NIH, National Institutes of Health directors, that genetics loads the gun and environment pulls the trigger. And that's one of the things that you're looking at here, is how is environment affecting human health. So enjoy yourselves today, enjoy your presentations, and we hope that you have a very rewarding experience from this whole year-long process. Thank you.
Okay, so just a quick rundown on today's agenda. So I think we have about 18 presentations today, and the presentations are 5 minutes long, so we'll do 9 presentations before the break, take a quick break, and then we'll do the remaining presentations. We'll do a lunch. We have Subway sandwiches today, so lunch from 12:40 to 1:25. We're going to do some quick evaluations as soon as you guys come back in, and then we'll pass out the goodies. So a little bit of background, just a couple of slides because I think it's important, at least for some of the teachers that are here and some of the judges too, to remember where we came from and then where we're currently at right now. So this program actually started with one junior chemistry student at Big Sky High School. And if I say the name of the school, feel free to clap and cheer. So one student from Big Sky High School actually started the program, Isaac Schmidt. So he's probably graduated and almost retired by now, right, Dave? Med school, yep. So he's doing pretty well for himself. So the program the following year went to additional classrooms within Big Sky and then additional schools the following year. And as of this year, we have about 1,000 students participating in the program, just like you guys, and throughout Montana, Idaho, and Alaska. This is the lineup for this year just in the state of Montana. So Big Sky, Sentinel. All right, represent Corvallis High School, Libby High School, Whitefish. Well, nobody's here from Whitefish, but so Whitefish, Butte Central are part of the program. They had their own individual symposiums here recently, and Hellgate High School. They actually were coming up until a couple of days ago, and they had a catastrophic computer failure with all of their data on the computer. So if there's an important lesson besides where the bathrooms are that you take home today, is always back up your data, no matter what it is. So Hellgate was not coming today, so they had about 40 or 50 kids participating in the program. So we also have expanded the program up to Alaska, and this is what is known as air toxics under the North Star in Alaska. And as you can see, we have a pretty good representation of where we're at in Alaska. Let's see. So we were here just a couple of days ago in, excuse me, in Quinhagak, Napaskiak, and Tununic. So this is the Bering Sea right there. Has anybody ever seen Deadliest Catch on Discovery Channel? Yeah, the crab. So those boats are like over here somewhere, and you know we were right there on the edge of the Bering Sea. And this is the Copper River area. And this is the Arctic Circle up here, Nuiqsut and Kobuk, and down all the way down to southeastern Alaska. So the program is actually doing very well up in Alaska. This is the third symposium that we've had in the last 3 weeks or 2 weeks. If I scroll back here, these communities right here had a virtual symposium. It was hard to bring all the kids from the different communities into one location like we are today. So we had a virtual symposium. So the students got up just like you guys are going to do today and get up and present their findings, and just like you guys are doing, except 3,000 miles away up in the Arctic Circle. And then this is another one that was in the Copper River area just a couple of weeks ago, or last week. So this is by far the biggest symposium that we have each year. This is, like I said, the 8th annual symposium. Past student winners. So if you didn't know by now, we actually give away first, second, and third prizes. Okay, so 2009, we had the effects of cooking methods on PM 2.5 and indoor air quality. So Cassie Moog and her sister, her twin, Cassandra Moog, they actually checked you guys in. They are from Libby High School, or former graduates of Libby High School, and have now come to University of Montana, and Cassie's been working with them in our lab for the last 3 years since she's been here, and doing very well. So that was a couple years ago, Libby High School. One thing I did want to point out, this kid right there, so keep your eye on him. Because Brandon Shannon, does anybody know Brandon? You know Brandon? So Brandon was, at this time, he was a junior, and he won the symposium all by himself, predicting temperature inversions with an artificial neural network in order to predict air quality. So that was when he was a junior. The next year, he came back as a senior, different project, roundabouts compared to traditional traffic light intersections and their implications on air quality, again by himself. So he is the two-time defending national champion for the air toxics under the Big Sky Symposium. Thankfully for you guys, he graduated, and he's now an economics major here at the University of Montana. So who's it going to be this year? So you guys feeling pretty good about yourselves? Yeah, you think your odds are pretty good? Okay, we'll see about that. We'll see about that, because we have a panel of special judges that are going to evaluate your presentations and your projects. Before we introduce the special panel of judges, just the ground rules for the poster sessions that are going on. So who else is presenting a poster out there? Okay, so I think we have close to 30 posters, give or take. Poster judging is going on right now at 11 o'clock. They're going to come in here and they're going to tell me who the top 6 posters are. And then we're going to go to break, and whoever, if I call your name, you stay out there by your poster, and then the poster judges are going to interview you, okay? So from that, if you're the lucky 6, you stay back out there and you get to come in for lunch later on. So there's prizes for the top 3 posters, first, second, and third. Third place gets $50, $75, and $100 for the top prize, and these are gift cards to the university bookstore. As far as presentations, I think we have 18, maybe 17. You'll get 5 minutes. So the way it'll work is we'll pull up your presentation, and then you guys come down. We don't know what the order is. We're just kind of winging it up here. So if we pull up your presentation, then you guys come down here, and then you'll have 5 minutes, okay? And then 2 minutes for question and answers. We have the top, the award is $150 for the University of Montana gift card for the bookstore, $125 for second place, and $100 for third place. So like I said, we have a special group of celebrity judges that we brought in to evaluate your presentations and to judge your presentations. And I'll start with Ben Schmidt. So Ben, go ahead and raise your hand. So Ben, you may have seen him on TV all the time. He's the kind of the guru for air pollution, air quality here for the city of Missoula. Anytime there's a wildfire, Ben's on the TV talking about, you know, what we're supposed to do. So Ben has a background in math, I think, from St. Olaf, and then a master's degree from University of Montana in environmental policy. And Ben has been at the health department here since 1991, and he's a really good skier and a great runner too, just as an aside. So Ben has been here, I think, this 4, 5, 6 years for as a judge, a long time. He's a veteran. So so welcome, Ben. So our next judge is Dr. Erica Woodall. So Dr. Woodall is an associate professor here at the Department of Biomedical and Pharmaceutical Sciences. She has a Bachelor of Science in Biochemistry from Notre Dame, and then also a PhD in Pharmaceutics from the University of Washington. So please welcome Erica to the program. And this third guy, you may not recognize him now, but you've probably seen his alter ego, who's Gee Whiz, or Garen the Wizard. So Garen travels around the state of Montana and throughout the Northwest giving magic shows and educating students on chemistry and getting people excited about science. So Garen received his PhD from Colorado School of Mines and has been up here at the University of Montana for a few years, and he is the reason that I came up to the University of Montana, in addition to the mountains and, you know, fly fishing and camping, backpacking, etc. So Garen was my advisor when I was in PhD or graduate school back in the day. So welcome, Gee Whiz. So this next couple of folks have been in your house several times. So Heidi Miley has been a judge for 4, 5 times. Last year she gave the opening remarks. Heidi has a BA in English education and also a master's in communications from the Edward R. Murrow School of Communication at Washington State University. And she's a co-anchor for KECI, and like I said, you've probably seen her many times on the TV at night. So welcome, Heidi. So Russ Thomas, you may have to wake up pretty early to see Russ. He's on TV he's a meteorologist for KPAX, that's the CBS affiliate. He's on very early in the morning, and he said that on a regular day he wakes up at 2:30 in the morning to make it to work on time. That sounds painful. So Russ has a Bachelor of Science in Meteorology from Florida State University, and he's been up here since 2003. Yeah. And we've been on the same softball team a couple of times, and he's an outstanding shortstop. So welcome, Russ. And last but certainly not least is Nancy Mora. So, yep, Nancy. Not yet. So Nancy was a honorary celebrity judge last year, so this is her first time being an official judge. Only because Nancy was on this side of it for the past 6 or 7 years. She worked for the Center for Environmental Sciences, putting on the symposium, and she's since gone on to bigger and better things in the education department here at the University of Montana, where she's the Director of Field Placements and Student Teaching. So Nancy Marr, thanks for coming. All right, it's go time. So what we're going to do now is we're going to load up a presentation, and when that happens, Cassie is going to be the timer, and Cassie's going to handle the lights. So you want to come down here and help with the lights, please? So we're going to load up a presentation. You guys come down, and then we'll set the timer. You have 5 minutes, and then after that, the lights will come back on, and then we'll ask questions.
Is it on? Yeah. Well, I'm Casey Stewart. I'm Courtney Elbert. I'm Elizabeth Hennessy. And we did our project on the air quality of various ways of making popcorn. And we're from Corvallis High School, and our teacher is Mr. Hamill. So the question we asked ourselves was, which method of preparing popcorn affects the air quality the most? So our hypothesis, we predicted that air popping popcorn will affect air quality the least, because when you prepare it this way, it doesn't require the use of oils that can start to smoke at their certain temperatures, which can affect the air quality.
Before beginning our experiment, we researched the health facts for each type of popcorn we use. As you can see, 1 cup of stovetop popcorn has the highest amounts of sodium and calories due to the amount of oil and butter used. And air pop popcorn has significant differences in the levels of sodium and calories because they're not those extra additives. And microwave popcorn falls in the middle.
We also researched what causes the popcorn to pop. The water, which is located in the outer shell, when it reaches 450 degrees, pressure builds up and the kernel turns inside out, and the popcorn is made.
So in our hypothesis, we mentioned the oils that have certain smoke points. So we researched which type of popcorn contains certain oils. So microwave popcorn uses palm oil, and the smoke point is at 446 degrees Fahrenheit. Air pop popcorn has no added oils. Stovetop popcorn uses semi-refined canola oil, and the smoke point is 350 degrees Fahrenheit.
These are the steps we took to carry out our experiment. Prior to the test, we tested the air quality in our controlled environment. During the test, we prepared popcorn according to directions of the preparation method and recorded the air quality using the dust track. After the test, we recorded our results.
These are our results. The x-axis represents the 10-second time intervals when each test was taken, and the y-axis is the levels of PM 2.5. This was our EPA, and these lines right here are the 2-minute interval time before we started the test. And then, as you can see, when the test began, air popped stayed well in here, while microwave and stovetop rose higher up into the PM, having a higher PM2.
So in conclusion, our hypothesis was correct. Preparing popcorn with an air popper affects air quality the least because it doesn't require the added oils that corrupt the air quality once they achieve the temperature of their smoke points. So we also wrote a little poem in conclusion. So when you're craving popcorn, air pop it nice and warm. With air quality clean and bright, it'll warm your heart with great delight. So there's no other way to make it, and you have to just admit that there is nothing sadder than breathing particulate matter.
In every experiment, there is always room for improvement. The changes we could have made were longer testing times, we could have done more tests, and we could have had more time in between each popcorn test, and we could have recorded a control before each of our popcorn methods.
So questions?
So your graphs of the particulate levels showed the solid red line. That's the EPA guideline for good air quality. And it looked like indoor air quality was higher than that before you did any of the popcorn tests. So were you breathing bad indoor air before each of your tests?
I have a wood stove in my house, so we think that may have affected it.
So how much time did you leave between each experiment?
Before each test, I had a 2-minute time before I started each popcorn. Then I started the popcorn and I gave it about a 20-minute time, and then I ended the test. Then I gave it another 20 minutes before I started each test.
Yes.
Okay, so what I'm curious about is like the microwave test. So do they think that like one person could have any time talking to the microwave? So what do you have the best track when you were talking to the microwave popcorn?
I had about a 4-foot count. I kept about 4 feet away from each test. I had it, 4 feet away from each test.
And the particulate matter, like she said, she was wondering since it would get stuck inside the microwave, but then we also took it out of the microwave and opened the bag and poured it out to see what else was in there once we opened the microwave. Any other questions?
All right, nice job.
Okay, hello everyone. I would like to start off by introducing myself. My name is Kyle Bruster. I'm from Big Sky High School and my teacher is David Jones. The title of my project is Difference of Particulate Matter at Roundabouts in Stop-Controlled Intersections. So when I began my project, I asked myself the question if what types of intersections would improve air quality, roundabouts or stop-controlled intersections. And I asked this question because Missoula suffers from many air quality problems, so I was wondering if intersections could improve those. So to answer the questions, I used 2 instruments, a dust track, which is shown right there, and the Q track right there. The dust track measured PM 2.5 levels and the Q track measured carbon monoxide levels, as well as other ambient things such as humidity and temperature. So I then selected 2 Missoula intersections. The first was the Higgins-Beckwith roundabout. Here's an above image, and here's the roundabout taken from the data collection point where I gathered my data. The traffic count here is 10,300 average daily traffic. And the second intersection was the Higgins South Avenue intersection with 9,500 average daily traffic. So I selected these 2 intersections because of their location along the same avenue here, Higgins Avenue, the short 9-block distance between them, and the similarities between traffic counts. So after selecting these 2 intersections, I developed an experimental design. I started by establishing a 7-hour overlapping testing period because of battery limitations and such. Then I selected a 1-minute logging interval. I locked the attachments in the car with the attachments outside the window there, making sure they both had adequate airflow and they were both gathering data. So after designing the experiment, I developed my hypothesis, and that was that roundabouts would improve air pollution levels compared to stop-controlled intersections because of their simplified travel, ease of navigation, and the constant motion of traffic, which should reflect itself in lower PM 2.5 levels. So after gathering data, I came up with these results here. Along the x-axis is the time from 12 p.m. until 6 p.m. And along the y-axis here is the PM 2.5 from 0 to 0.12 milligrams per cubic meter. Compared to the next graph of the stop-controlled intersection, it has a much steeper linear trend. This linear trend does not include these outliers at the ends that only have one test. So it has it paints a more accurate picture of the particulate at the intersection. And here are the results from my stop-controlled intersection. Along the x-axis here is the time from 10 a.m., so it started 2 hours earlier, and it ends at 6 p.m. And along the y-axis is the PM 2.5 in milligrams per cubic meter from 0 to 0.1 at the top. As you can see, the average is much more linear there, and there's also a lot less spiking over the course of the day. So to visually compare these two, here's my roundabout, here's my stop-controlled intersection, and here is the roundabout overlaid, and now it's really apparent that steep change in particulate throughout the day. All of my averages for this test fell within the highlighted area here. So I used the EPA's air quality index to analyze my data. All of my averages fell within the orange unhealthy for sensitive groups area. So as you can see, both intersections had unhealthy levels. The roundabout having 61 micrograms per cubic meter, and the intersection having 55 micrograms per cubic meter. The difference of 6 micrograms per cubic meter can be considered negligible due to environmental variables and such that could not be controlled for. So therefore, my hypothesis was neither proven or disproven. However, results from my study can be expanded upon, and it can help people and organizations plan better intersections. So to address issues in my study, I plan to conduct further research by incorporating more ambient results into my data, as well as changing my testing periods and locations to better understand the pollution at the two types of intersections. So here are the references I used, and I would like to thank many people, including David Jones and Kate Linsner from Big Sky High School. So, thank you. Yes?
Can you explain the AQI, one of those slides you had, AQI?
So, explain the air quality index. Sorry, here? This one. Oh, so the air quality index value is when you plug in these two numbers here into this, the air quality index website. It will give you a number, and so you can look at that number in the table here. And so both of them were from 100 to 150 there, so they're in that unhealthy group. Are there any more? Yes?
I couldn't tell from your presentation, maybe because I wasn't listening closely. Did you do the measurements at both intersections on the same days? Or did you, because of equipment limitations, have to do one intersection one day and the other intersection the other day?
When I started my data gathering, I only had one set of equipment. So 2 of my tests only had one at each, but I flip-flopped them. So I had one on Saturday, and the stop-controlled intersection on a Saturday, and then the next time I tested, I did it on a Sunday. But then later on, I had 2 sets of equipment running at the exact same time. Yes.
And did you see a difference when you did simultaneous sampling versus alternating days?
Not really. Kind of on average, they stayed about the same, but Sunday traffic and Saturday traffic are a bit different, and so. But I think they averaged out to be about the same. Yes?
Were the samples collected on the same quadrant of the intersection, by then like the southwest corner on both times? Or?
No, they weren't. One of them was gathered at the southeast quadrant, and one of them was kind of on the west end of the roundabout. Don't really know if there are quadrants on the roundabout, but so they were on opposite ends. So when I do do further study, I kind of want to look at the air quality at different ends of the intersections, because to see if, like, you know, wind and such are affecting my results.
Why do you ask that? Why do you ask that question?
Because an interesting phenomenon is if you go to opposite sides of the street, you'll get quite different results. If you like try to do residential sampling, for instance, if you go 2 blocks off Reserve going to the east, you'll tend to get much higher results than if you go to the west in many parts of town, just because of the natural flow of air.
And that also could explain why I had higher roundabout particulate levels, but there was a higher traffic count at the roundabout too. So I just want to do further study to understand that better.
Thanks, Carl.
Thank you.
All right, my name is Morley Jessup. This is,
I'm Miles Wickham.
and we tested the effects of welding on PM 2.5 levels. We're from Cross High School, and our teacher is Mr. Hamill.
Question we asked is, does welding affect the PM 2.5 levels in the facilities, and does it make it unhealthy?
And our hypothesis was when welding, the PM 2.5 levels will rise above the recommended level of 35 micrograms per meters cubed because of the PM 2.5s emitted by the incomplete combustion of carbon-based gases.
Our procedure was we took a test 30 minutes, a test of 30 minutes before any classes were in the welding shop. And then we waited until there was a welding class, and then we tested for another 30 minutes to see the difference.
This is our welding room, and right on the left side, you can see on the left of all the pictures is where they weld. So
these are the PM 2.5 levels from before class. The blue line here is the EPA recommended levels of 35, and as you can see, they didn't really spike above too much, just once or twice in the beginning, but for the most part it stayed pretty healthy for the 30-minute period.
and then this one's, as you can see, way above, and that's when we were welding. For the most part, it stays above that, above the 35 recommended level, and it jumps all the way up to like 369. So that's a lot higher. It's like 4 times the average of before class. So
These are the combined graphs. The red down here is before class and the orange is after class, so there's quite a big difference between the particulate matter. So it looks to be unhealthy.
these are comparing the averages. The average with class was 63.94, and the average before class was 12.66. That's almost 4 times, 4 to 5 times, as I've already suggested. And then the max with class, it jumped all the way up to 369 at one point, and without class, it jumped up to 52.
Our results was our hypothesis was correct. When welding, the particulate matter levels are over 4 times the average when not welding, which is far above healthy. And the maximum levels were over 10 times, reached up to 10 times that of the EPA recommended amount of 35 micrograms per meter cubed.
Improvements, we could have done longer testing periods and more tests, and we could have controlled how many times each weld, how long each weld, what kind of weld.
And we could have tested other welding facilities, like at other schools or something, and then test different kinds of welding, arc, wire feed, and oxyacetylene gas, and also do future research about possibilities of improving the ventilation systems in welding shops.
Any questions?
period is that EPA recommended amount?
It's for over a 24-hour period.
Right, so how long do you think during the day you had readings above that level?
Well,
How long was it above the level? Throughout the whole day, pretty much. As school starts till, I'm sure, a few hours after school at least.
So who at the school was probably most subject to the problems with the air pollution being higher?
probably the teachers and the kids in the class.
Right. Teacher more than the
Yeah,
kids, 'cause they're just in and out.
yeah, he spends most of his time in there.
He spends the
Right.
whole day in there, so. Any more questions?
Do you know or at least suspect what particles cause an increase in air quality?
Can you repeat the question?
Do you know or suspect any particles that specifically cause the increase in high levels?
No, we don't know the answer to that.
In class, are the teachers and students wearing any kind of personal protective gear? And if not, do you think based on your data you would recommend that they should?
Yeah, they wear some leather jackets and gloves and welding masks, but something that could help with this is wearing possibly even just a small dust mask or something like that.
But no, they don't wear dust masks.
I have one question. Is there a ventilation system inside the?
Yeah, there's a ventilation system inside.
It's just one vent that ventilates the whole room, so
Yeah.
could be improved. Any more questions?
Yeah, one.
Our project was the effect of foundation design on radon levels within the home. I'm Emily McBride.
I'm Alyssa Walker.
And I'm Tana Wilson, and we're from Libby High School under the instruction of Mr. Gene Reckon.
Radon is a colorless, odorless, tasteless inert gas that is formed by the natural decomposition of uranium in the soil. As it decays, radon is released by radioactive byproducts that are emitted from the ground and enter the home through cracks in the foundation, walls, basement floors, and other openings in the home.
This is a distribution map of the United States that shows the potential radon levels in particular areas of the country. Note that low is at 2 picocuries or less. Yellow is moderate between 2 and 4 picocuries, and pink is high at 4 picocuries or more. And when you reach 4 picocuries, that's when you need the health concerns begin to arise and mitigation is recommended. You can see most of Montana is pink, but keep in mind that that's the potential, and that's not virtually, there's no risk outdoors. But enclosed areas should be monitored regularly.
The health effects caused by radon are virtually undetectable without medical testing. It is the second leading cause of cancer with 21,000 deaths a year. In a hypothetical situation, if 1,000 non-smokers were exposed to 20 picocuries per liter of radon, 36 could potentially get lung cancer. If you were to take 1,000 smokers and give them the same amount of radon levels, potentially 260 could get lung cancer. This shows the multiplicative effect of radon and smoking.
The question we explored was, does home structural design increase the accumulation of radon and thus the exposure to occupants of the home?
Home construction is an important factor when dealing with levels of radon in the home. We tested 3 basic structures: basement, crawl space, and slab, mainly focusing on how air is circulated throughout the home and how air is vented in and out of the home. This is a basement, it's a picture of a basement, and it has, basements hold great potential to hold radon if they're not ventilated properly. Radon can enter the basement through cracks or unfinished parts of the basement. Any source of circulation can prevent high levels, such as a fireplace or a dryer, because they're going to be venting the air.
The average crawl space is 4 feet tall and usually has a 6 millimeter plastic ground covering. It is recommended to have ventilation in your crawl space because without ventilation, there's a higher risk for radon to accumulate. With the ventilation helps circulate air out, and cracks in the floor may allow radon to enter the home. It's living space.
As you can see, a slab has only one layer of foundation protecting the ground and the living space. This gives it high potential for accumulating radon within the living space itself.
For our hypothesis, we expect homes with full basement foundations to have higher levels of radon with crawl space and basements. Higher levels of radon than homes in crawl space and slabs. This is because ventilation in basements is less and radon has a greater area to settle.
We began our testing procedure with a questionnaire in which we obtained more information about the home, such as the age, their feet, and the source of home heating. We placed a monitor 4 to 6 feet from the ground and 2 feet from electrical devices, all within the main living space.
We used a t-test to analyze if there was a relationship between each structure's radon level. We compared slab versus basement, slab versus crawl space, and basement versus crawl space. If the results are above a 0.05 number, then it suggests no numerical relationship, and our data is above the 0.05 number. Under the chart is the average radon levels for each structure, and the average slab level is higher than the others, which does not support our hypothesis. Our t-test scores show that there is no relationship between foundation structure and the level of radon within the living space. This could be due to our small sample size of 12 homes tested, 5 crawl space, 5 basement, and 2 slabs, because slabs were really hard to find. Based on our averages, we hypothesized that crawl space and basements accumulate radon similarly. This suggests that ventilation may help filter out radon, and which may be why living spaces with slabs tend to have higher levels of radon. Further testing would be warranted to test our hypothesis based on our findings. If we were to redo our project, we would recommend testing within the same vicinity.
We would also recommend similar home structures, such as the building materials used in the home, the square feet of the home, and air ventilation methods used.
Even more, a larger sample size with equal number of structures tested would make our data more reliable. Same weather conditions such as barometric pressure or same season time of the year may also have an effect on our results. Questions?
What was the floor of the basement made out of? Like, was it made out of dirt or was it cement?
It varied. Mostly it was cement, and usually you had finished basements. Most of ours were finished.
And did your test results vary depending on if it had a dirt floor or not? So, like, was it higher because of it was a dirt floor, or was it lower because of it?
You know, we can't really make any conclusions, but it mostly depends on the ground you're on. I'm thinking it comes from, I don't think it has anything to do with the basement foundation.
Did you try to get a hold of any geological information in the area where you did your testing?
We did. Part of the problem with radon is that it tends to be in pockets. So if you were to take a grid of our city, for example, one neighborhood may have high levels of radon, while another may have virtually none. So our neighborhoods were scattered out, which doesn't give us a clear reading exactly for results.
Yeah, and then how does the radon get up to the house?
Into the home? It comes from different cracks within the foundation.
But crack systems in the earth too, so I was wondering if there was any studies that have been done on the subsurface as far as any fracture systems there.
Not that we're familiar with.
I just have one question. You said you did this test in living spaces. Were they all like consistently far from any doors that may be opening and closing, or were they sometimes in bedrooms or other rooms?
Yeah, you know, we put them away from electrical devices like phones and computers and doors, like anything from like windows and doors. We try to put it in a space and 2 to 6 feet from the ground, I think. So we tried to do it as best as we could, most accurately.
Thank you.
Thank you. I gotcha.
My name is Louis Seelock. My name is Jesse Nelson. From Libby High School, and our test we see the effects of the location of a wood stove on air quality in the home. We wanted to see if the stove upstairs or downstairs affected the PM 2.5 levels in the home, and also wanted to find easy fixes to indoor air quality issues. Our hypothesis was to see the concentrations of PM 2.5 levels would rise with heat, causing greater levels upstairs.
In our procedure, the stoves in his home are identical stoves running on the same chimney line. We tried to use equal amounts of firewood with a 24-hour testing period with data collected every 60 seconds. We set the damper the same, and our monitors were running simultaneously 10 feet from the stove and 3 feet from the ground.
This is a test from October 28th with the fire lit only upstairs, which is shown in red. This is a test from November 8th with the fire lit only downstairs, which is shown in green. This is a test from November 9th with the fire lit both upstairs and downstairs, which is shown in red and green. This is a test from just a couple of weeks ago with the with no fire lit upstairs or downstairs, and we use this as a control. In this one, you can see that like these two are pretty similar. With both of these, the fire weren't lit, and then in both of these, the fire were lit, which is pretty similar. And this is our control. These two.
Our conclusion is that there's no direct correlation between where the wood stove is located in the home. So you should just put your wood stove wherever it's convenient for you to get your firewood in. So. Any questions?
Any questions? Oh.
Yeah. Your traces seem to have sort of a low reading and then an abrupt spike which tailed off. Was that when you opened the door to stoke the stove?
Yeah, it would be like every time, and like sometimes it was just, I try to keep the like activity in the home the same, so like my dad might clean or cook dinner or something like that, but it was just like a variety of things would spike it, and then it would drop off after it like washed out. Is that everything?
Hello, I'm Rachel Lindley.
I'm Michaela Fiore.
And I'm Darby Moss. And we're students at Big Sky High School under the instruction of David Jones. For our project, we decided to test air quality in restaurants.
When we came up with the question, we decided to ask what the difference was in air quality and PM 2.5 in different restaurants, and we tested for the max air quality in each restaurant. We decided that we thought fast foods would have the highest max air quality because of the poor cleaning in the facilities and because of the greasy foods, which most fast food restaurants have. And then we also thought that Italian restaurants would have the lowest just because of the type of cuisine they have, because of the pasta and things. We thought it would be less PM 2.5.
So our methods for our data collection, we decided to choose 4 different types of restaurants and go to 2 restaurants for each category. We chose fast food, Italian, American, and Asian cuisine. And for each restaurant, we tested for 30 minutes. So here are our results for the fast food. We wanted to look at spikes because our instructor brought it up to us that each restaurant has pretty much the same average ambient air quality. So we wanted to focus on different spikes and changes within the graphs. Next one. So this is our second fast food restaurant. There is a big spike in the middle, but it stays pretty much the same. For Italian, our first data collection, we're not really sure what happened here, but it was a little messed up. But for our second Italian restaurant, we got some very large spikes. As you can see towards the beginning of the graph, we have a spike that is over 0.7 PM 2.5 levels. These are our American results, which have spikes, but if you look at the x-axis, which is the, or the y-axis, which is the PM 2.5 levels, it is actually fairly low. This is our second American, which is pretty much the same as our first. And these are our Asian cuisine results, and they also have fairly low levels in the spikes. And here's our second one. So, we concluded the American restaurants had lower levels of PM 2.5. The Italian restaurants had higher, or significantly higher ones. Our maximum PM 2.5 level was 0.708 milligrams per cubic meter, or 708 micrograms per cubic meter, and that was in the Italian restaurant. And the national indoor restaurant limit is 15 micrograms per cubic meter, so that spike was fairly above. So our conclusion is the American style cooking creates the lowest levels of PM 2.5, and Italian style cooking creates the highest levels of PM 2.5 and spikes. And we trace this back to the opening and closing of oven doors when taking out pizzas or whatever they cook in ovens there. And we also thought that it might be the location of the kitchen within the restaurant, because in the Italian restaurants that we went to, the kitchens were very open, and as opposed to the American restaurants where the kitchens were further back in the restaurant, far away from the dining area. So these are our references, and any questions? Okay.
Yes. I have to ask, when you say the American style of cuisine, could you explain exactly what you mean? Because that can mean a lot of different things from Hoboken as opposed to some of Baton Rouge. What do you mean by American style?
Yeah.
We tested usually like sit-down restaurants, which cooked things like burgers with like fries and things like that, as opposed to like an Italian or Asian restaurant.
Do you think your results would have been illustrated differently if you had a longer testing period?
Of course they would be. I think the graphs would be a lot more leveled out with the spikes periodically, and probably depending on the time of day, if it's during dinner time, it probably has a lot more spikes as opposed to early afternoon where people aren't dining as much.
So with your tests, were you run all your tests at a similar time during the day, during similar level of activity in the restaurant?
Yes, we usually went around lunchtime, so between 11 and 2 o'clock.
What would be the difference from an American restaurant and an Italian restaurant based on
Based on cuisine or just the results?
Yeah. How would they get, like, based on the results, yeah?
Based on the results, we found the Italian restaurants did have higher levels when they spiked, and we traced this to opening and closing of oven doors when cooking pizza, as opposed to the American restaurants where they used a lot more barbecue. And we also thought the kitchens themselves were further back in the restaurants.
So it sounds like you evaluated customer exposure. In another test, would you, for example, evaluate the exposure of the employees in the back?
Yeah, that brings up an interesting idea. We did evaluate customer exposure. We didn't get a chance to go back into the kitchens, so that would be very interesting to see how each kitchen differs.
Was it awkward when you put the back on and like people were watching TV and the machine was going?
We had the machine in a bag so people wouldn't question us because we didn't really want to have to explain.
You had your PM monitor in a bag?
Well, we had, okay.
So we had tubes that we could connect to the machine, which would come out of the bag, and we would lay the tube on top of the bag to test the air, like, out in the open.
Don't worry.
But which had the best cuisine?
Probably the Italian.
Definitely the Italian.
Yeah.
So what were the specific restaurants that you tested?
We're not supposed to tell the exact restaurants just for confidential reasons.
Yes.
Yeah, one quick question. Was the flooring different in the different restaurants? Carpeting versus linoleum versus whatever?
They were mostly carpeted, from what I remember. I think they were all very similar one-level restaurants with carpet.
All right, nice job.
Good morning, my name is Michelle Nemetchek.
And I'm Stacia Hill.
And our project is the investigation of harmful particulate matter present in various aerosol air fresheners. Aerosol air fresheners are commonly seen throughout households today, and many popular commercials depict consumers dousing their living rooms with air fresheners and breathing in deeply the manufactured fresh linen scents. But how safe is this action for sensitive groups? Especially when indoor air has poor circulation, particulate matter inside the home can be of even more concern than outdoor air quality. Studies show the use of aerosols indoors could potentially result in increased concentrations of harmful particulate matter as a result of ozone and limonene reactions. To assess the safety of air fresheners, we decided to use the Outdoor Index to discuss harmful particulate levels, since the EPA has not yet set indoor safety levels for PM2.5. As seen here, the outdoor levels for PM2.5 range from good, at no particulate, to at least 0.334 milligrams per meter cubed, where levels are labeled as hazardous for all groups.
For our first test, we wanted to see if an average spray of a common air freshener, such as Febreze, would cause harmful PM2.5 levels. We hypothesized that in a soft surface room, such as a bedroom, Febreze would not cause harmful levels of PM2.5. To test this, we sprayed 10 milliliters, which was equivalent to about 12 seconds of sprays of Febreze air freshener evenly throughout a bedroom. Our dust track was placed about 4 to 5 feet above ground, and we focused on the measuring of PM2.5 and set the dust track to log data every minute. Here are the results from our first test. This time we turned on the dust track directly after spraying Febreze, which failed to give us an initial level of particulate, so we ran the test again. Here's the second trial, with all the same variables. By looking at this graph, you see the PM2.5 briefly raise into the unhealthy zone, but quickly decrease after only a few minutes. When looking at this data, we saw Febrze's potentially dangerous effects were very temporary, and particulate returned to the initial level after 3.5 hours.
We then wondered if the type of room would affect PM2.5 levels, as rooms with hard surfaces are easier to clean, and could potentially have less solid particles for Febreze to combine with and create harmful PM2.5. We hypothesized that a hard surface room, such as a bathroom, will have lower PM2.5 levels than a soft surface bedroom. Keeping all other variables the same, we moved to a hard surface bathroom and performed the same test. Here are the results from there. By looking at this data, we saw Febreze raise PM 2.5 levels to the moderate safety level, and after 1.5 hours, levels had returned to their initial state. Compared to the previous 3.5 hours in a soft surface bedroom, we could conclude that PM 2.5 levels of Febreze decreased quicker in a hard surface area, possibly due to less solid particulate.
We then wanted to test if different types of aerosol air fresheners changed the particulate levels that were being created. We hypothesized that a cheaper, less well-known brand of aerosol such as Airwick would cause more PM 2.5 than Febreze. We went back to the soft surface bedroom and sprayed 10 milliliters of Airwick air freshener. Here are the results from this test. Very briefly, PM 2.5 levels raised to the unhealthy level. However, that quickly decreased, and after 1.5 hours, PM 2.5 levels were back to their initial state. Although Airwick elevated PM 2.5 levels a bit higher than Febreze, the particulate matter appeared to dissipate faster, which may make Airwick a safer brand for use in households with sensitive groups. According to our data, hard surface rooms are slightly safer for sensitive groups when spraying air freshener, and Airwick raises PM 2.5 levels for less time than Febreze, possibly making it more ideal air freshener in households with sensitive groups. In our study, we concluded that levels of PM 2.5 produced from the use of aerosol air fresheners are rather low and not likely to cause harm. However, to avoid any potential risks associated with the use of air fresheners, we suggest stepping out of the room for a few minutes immediately following the use of air fresheners to allow PM 2.5 levels to dissipate. Thank you for your time, and any questions?
Yes.
Can you go back to your conclusion about the
Febreze raised the PM 2.5 levels to a lower level, but the particles tended to stay suspended in the air for a longer amount of time, whereas Airwick had a higher level of PM 2.5, but it dissipated much quicker.
You have to check the contents, ingredients that we are making that comparison.
Many air fresheners don't specifically list a lot of their ingredients, kind of because of their specific formula. They don't want to get out to the other producers, so we did not compare those.
What's better, a large amount over a short period of time, or a less amount over a longer period of time? What's better for you?
We didn't test different amounts of air freshener. We tested the same amount of liquid in the air both times, but if we were to do this test again, we might possibly vary the amounts of hours.
And like Michelle said, we didn't specifically test for this, but I would recommend a larger amount over a shorter period of time, because from our data we did see that even if the air freshener raises the particulate matter, it does tend to dissipate rather quickly. So that seems to be a safer method than to reapply continuously over a long amount of time. Yes?
You might have already stated this, but I was just interested. Did you close all the windows when performing this test?
Yes, in both of the rooms, they were closed off areas that had minimal human interaction in them, so the environment was pretty stable. Skylar?
Were the rooms like the same size? Because bathrooms are usually smaller than bedrooms.
There was some size difference, so the bathroom was probably about a half the size of the bedroom, so that's something to consider.
How did you measure 10 milliliters from an aerosol?
So we gauged it about 10 to 15 seconds of spray is the average for, at least personally, how much I spray air freshener in my room. So we took a specific air freshener and sprayed it into a bag with the end of the bag cutout, and that funneled into a little collection cup in which we could measure the amount of liquid that comes out per second. So then we could compare the amount of liquid coming out of both Febreze and Air Wick.
Dakota?
As an air freshener consumer, I'm interested to know, after the particulate matter is gone in the room, will my room still smell good?
That's something you might want to consider. It's my thought that as the particulate matter decreases, the smell might also decrease, which might explain why Air Wick is a cheaper, less popular brand, because the scent doesn't linger around as long, but also the particulate matter isn't going to linger around nearly as long. So it's a personal decision you need to make.
All right, nice job. So real fast, I'd like to acknowledge Stacya's in the past couple of months has done pretty well with the science fairs. So she cleaned up at the Montana State Science Fair, and then at the International Science Fair last week, she won $1,000. So nice job, Stacia. And Earl is now, Dr. Adams right there with the blue shirt. Earl, raise your hand. Earl is the director of the Montana State Science Fair, so he's scouting out future presentations for next year. So any juniors that want to come to the science fair, you know, you guys are more than welcome. And again, cold hard cash is involved. And the International Science Fair is in Phoenix, Arizona. So if you win the Montana State Science Fair, you get to go to Phoenix next year.
So my name's Marissa Sewell from Sentinel High School, and my project is a study of the effects of global warming on atmospheric pollen levels over time. I decided to investigate this project because global warming is really a popular topic in science, and millions of people are severely affected by seasonal allergies and asthma nationwide. These allergies can be caused and are worsened by aeroallergens such as pollen and mold spores and dust. And the amount of aeroallergens may be affected by temperature change, which leads me to my hypothesis that if the average temperature changes over time, then pollen levels in the atmosphere will change proportionally. So some studies have been conducted on this topic, but none have really explicitly stated a direct relationship. The temperature change that has taken place over recent years has drastically affected the reproductive systems of many botanical systems, including things like pine trees and grass and weeds, which can really irritate people with allergies. Longer and hotter reproductive seasons may cause an increase in pollen production, which can have several repercussions both in the environment and in society. So to investigate this, I acquired the average mean daily temperature for Missoula, Montana between the years 2006 and 2011 and compared them to pollen counts from the same time frame. And these pollen counts were acquired by the use of a Berkeley pollen sampler right there on the screen. And it basically intakes a small amount of air through a small hole into a circular chamber, and the chamber contains a small disc covered in grease tape, and after a week's time the tape is removed and counted under a microscope. The pollen is counted. And these are some examples of pollen under a microscope that one might see. So my results. This graph on the top depicts the change in amount of total pollen per year against the average change in temperature. I did not use data from 2011 because pollen was not available for that year. The bottom graph here represents the same two variables, and a correlation coefficient of 0.78 is there, which could indicate a strong correlation, semi-strong. This graph here represents temperature versus pollen for the year 2011, and this graph is similar to graphs for the other years that correlation exists. So in conclusion, there is a correlation between temperature and pollen both in 1 year and over several years. And as temperature continues to change as a result of global warming, it can be assumed that pollen production will change proportionally. So increased global pollen levels could lead to increased allergy frequency in all immunocompromised and some immunocompetent individuals as well. Incidence of adult onset allergy to pollen will also increase. People already affected by allergies, their allergies could worsen and the symptoms could be much more severe. So to continue this study, you could do a broader study of the relationship between temperature and atmospheric pollen on a national or a global level, because this was just in Missoula. The results of this study could also be used in an investigation of the relationship between increased atmospheric pollen levels and the number of people affected by allergies. So I would love to answer any questions.
How do forest fires affect atmospheric pollen?
Well, I didn't really investigate that, but I guess it depends on where you're counting the pollen, because if all the trees and grass are gone that produce pollen, then I guess there wouldn't be as much in the atmosphere. Yeah.
I don't know if you said, but do you do any research on why the pollen would increase when temperature does?
Yeah, as temperature increases, it lengthens reproductive seasons, or it can move them to different times in the year. And lengthen longer reproductive seasons or more intense reproductive seasons could cause an increase in pollen production. Yeah.
Is there any seasonal distribution over a growing period to the preponderance of pollen? Or is that not teased out in your data? Like when the pine is pollinating, a lot of times the air looks green at times. I just wondered if you saw any seasonal distribution in your pollen.
The end of June and early July was really the time where there was the most pollen in the atmosphere, and that usually came from pine trees and some grasses. That could change, though, if the summers got too hot and things stopped pollinating, or if winters weren't as intense, and then the grass would have a longer time to generate more pollen. Yeah?
So did you look at all at moisture? Did you add precipitation? Or how that kind of fit into the mix as far as longer growing seasons, if they were longer versus was there available moisture to grow those pollen producing the plants? Would you be able to, did that ever come up on radar at all to look at?
I didn't investigate precipitation as a variable, but there is a lot of environmental variables such as precipitation that could affect it. If I continued the study, I would investigate precipitation, as well as wind pollinating plants. Wind could also be a factor in the amount of pollen in the atmosphere. Yeah.
Hey, one thing I know, is Emily in here?
Yeah.
Yeah. Hey, and you can help me with this one too, because she helps me a lot with the certified pollen stuff that I do. So she helps me with the whole thing. But last year, we almost had no tree season, correct, because it was so cold for so long. And then as we finally got warmer, and that was probably late June, July, things started to spike, right? So really, I mean, that correlation, moisture-wise, anything there?
You know, increased moisture is going to increase the pollen production in general. When you have a dry winter like we do, and a long winter, it pushes everything back, and you'll get less pollen, and all of your peaks will be moved further.
But temperature definitely seems to be like a big player last year.
Yes. Yeah.
Now, did you, or if not, are you planning to examine comparing the pollen production and the increase in temperature? Have you at all correlated that to any increase in cases of asthma recently?
No, I have not, but if I continue the study, that's one thing I would investigate, because that affects a lot of people.
So that was Emily Weiler, CPC, Certified Pollen Counter. And Emily is the only certified pollen counter in the Northern Rocky Mountains, so that's Emily back there. And graduated of Big Sky High School.
Let's not judge them because they have the asbestos solution.
Woo!
All right.